let's start with the empirical rate of a reaction. So empirical rate of a reaction. So this empirical rate of reaction is the rate of a reaction. The rate of a reaction is usually proportional to the molar concentration of reactant raised to a part. So that is called the empirical rate of reaction. And what is a rate law? What is a rate law? So the rate law is just a mathematical expression relating the molar concentration of reactants to the overall rate of a reaction. So suppose there are two reactants giving us a product. So the rate we've already discussed. A to the rate n, b to the rate r m. So this is our rate constant, okay? And this m and n are the order of a reaction. Order m and n are order of the reaction, with respect to the concentration of A and B. And this order, we determine it experimentally. We determine it experimentally. And to determine the rate law experimentally, we use two methods. One is called the isolation method. And so, what is this isolation method? So, we know that in the isolation method, we isolate one of the entity and determine the other one. Meaning we keep one constant and we determine how the other one is changing with respect to that. And similarly, if we want to determine the rate law of B, we keep A, we keep B constant and we vary A. That's how we determine the in isolation method. So suppose we want to determine the rate of A to the bar and B. So we keep B as constant, and varying A, we determine the rate law. So how do we do that? So determination of the order of the reaction for this reaction for M, we just multiply both sides by, let's say, log. So log of rate is equal to log of K into A to the bar M and B. So this is equal to log of K to the A to the bar M plus log, B, since we're keeping B as constant, A, and we're varying A, so log of rate is equal to log K B to the bar N plus, in terms of logarithm, M log of A. So from here, this is our Y, and this is our C, and this is our X, and So we are getting a straight line function. Y equals mx plus c. And similarly for for getting a B, the concentration of B, we keep A constant and vary B to determine this R. So log of rate is equal to log K A to the power M B to the power N, which is equal to log K A to the power M plus log B to the power N. So again, we're getting the same function. Y is equal to mx plus c. X m. This is our m. This is our slope. So we're getting a straight line for this. Now we'll move on to integrated rate law. So what is integrated rate law? Integrated rate law. So for example, a reactant gives us products. Now we know that the rate of a reaction is equal to the rate of the reaction is equal to the disappearance of this reactant over time, the instantaneous rate of the reaction, or rate is also equal to the concentration of A raised to the power n. And if we integrate this, then we're getting the integrated rate law. So every reaction order has a unique integrated rate law expression. Therefore, since both are equal to the rate of the reaction, we can equate this as negative Tt of A is equal to A raised to the power n. Now, for zero order reaction, this one, when n is equal to 0, that means for a zero order reaction, anything to the power, sorry, this is K, the A, anything to the power 0 is 1, so negative d over dt of A is equal to just K. So integrating both sides, if we integrate both sides from the initial to the final concentration at time t, so we integrate both sides from our initial concentration A naught to A, sorry, we can move this up here, so right in the next step, integration of d of A naught to A is equal to negative K dt, integration from 0 to time t. So this will be just the difference between A naught, difference between the final concentration and the initial concentration. Negative KT. If you differentiate this, just get t done. So let's manipulate this one. T is equal to negative kt plus a naught. So now we're also getting here. Also we're getting mx c. So we're also getting a straight line. But how will it look if you plot? It's not straight. So since the slope m is negative, so we'll get a straight line but a negative curve because it's the sign is negative here, and our intercept here is our concentration A, because y is equal to A, and then here the x-axis is our time, and here is our intercept A naught C. So that is how our integrated rate law for zero direction will look like. So this is our expression. Similarly, for the same reaction, when n is equal to 1, that is for first order reaction, so our rate negative d upon dt of A will be equal to k into A raised to the power 1. So negative d A divided by A is equal to k dt. And we'll shift this negative towards the other side. And then on integrating both sides, from similarly from initial to the final concentration, time t, and from here 0 to t. So this one, if you differentiate this one, we'll get log, natural log of A from our initial A naught to the final concentration. Is equal to, if you integrate this one again, kt, just get kt plus some constant. So this one will be log of A t minus natural log of A naught is equal to negative ktt. So this is the rate law expression for the first order, and then we can make some changes in this equation. If we bring this out, if we bring a negative in, then we're getting log of A naught minus log of the final concentration is equal to kt. Then the property of log here is that if it is negative, we divide. If it is positive, we multiply. It's the product. So since this is negative, we'll divide this natural log of A naught over AT is equal to KT. So we'll bring this T down. So 1 by T natural log of A naught over AT is equal to K. So our rate constant K, and if we change this natural log to the base 10, then we have to multiply it with 2.303. 2.303 over T natural log to the base 10 A naught over A. So this is another way of expressing the rate law expression for first order. So we won't be focusing on the second and third order or fractional orders, but we'll do some numerical problems with this, the zero order and the first order. And again, you can look that if you move this negative log of A naught to this side, then we are getting y is equal to mx plus c, a straight line, but with a negative slope again. C because we have a negative here. So our graph will be negative, but straight line, and then here on the y-axis, will be the concentration of A time t. The x-axis will be our time axis. The intercept will be log of the initial concentration, and then our slope will be given by negative k. So that is how our graph will also look like for first order reaction. So and then we have integrated rate law for half-life. Suppose we'll check one of the other half-life. When the initial concentration becomes exactly half, or yeah, this is our half-life of a reaction. Our concentration becomes half. So at what time? So our expression for zero order n is equal to 0 is a t is equal to negative kt plus a naught. So this was our expression. Y is equal to mx plus c. Now, when this initial concentration exactly becomes half, that is our half-life reaction, time taken to half, time it takes to half the initial concentration of reactant. So half of the final concentration will be equal to negative kT plus A naught. But here our time becomes T half, because at time T half, this will also become half of the initial concentration. So our time T half will be given by negative half of A naught over negative of K, or T half for zero order is equal to A naught over twice K. So that is our half-life of zero order reaction. Now for a first order reaction, natural log of AT is equal to negative KT plus natural log of the initial concentration. So when this becomes half, log of half AT is equal to KT half plus natural log of A. So natural log of half AT minus natural log of A naught is equal to negative KT half. Now, since this is negative and we have log on it, the function of log states that, sorry, this should be initial concentration. Half of the initial concentration, sorry, I missed out on that one. So our A naught divided by A naught is equal to negative KT half. So this gets cancelled out. And now this one, log 2 to the raised negative 1 is equal to negative KT half. Or negative 1 log 2 is equal to negative kt half. These two goes off. So t half is equal to natural log 2 of over k. Now here you can see that in the first order, the d half, it is independent of the concentration of the reactants. But here zero order is dependent because here we have the initial concentration, but in first order it is independent of the initial concentration. So what, as I mentioned, if you want to convert this to log to the base, then you simply have to multiply it with 2.303 into 2 divided by k. So sorry, that is not. So log 2 is, yeah, 2.303 into the value of log 2. If you add, I forgot the value, then you get 0.69, I think, yeah, divided by k. So that is our final expression for the half-life of first order reaction. So here's a question. The first order reaction is 15% complete in 20 minutes. How long will it take to complete 60%? So we know that the rate of a first order reaction is given by 2.313 over T log of the initial over the final concentration. So if our initial concentration is equal to A and our final concentration would be A minus A into 15%. So 15% would be this one, which is equal to 0.85 A. That means 0.85 A is completed, and our time is given us 20 minutes. So we plug in those values. K is equal to 2.203 over 20 log of A over 0.85 A. So this will give us 8.13 into 10 raised to the power negative 3 per minute. And in the second case, if A naught is equal to A and the final concentration is equal to A minus A into 60 over 100, this is nothing but 0.40 of A or 60%. Now, time we don't know. So we'll plug in this equation because we know the rate is this much. So we'll plug in the values in this equation. 0.303 over 8.13 into 10 raised to the power negative 3 log of A over 0.40 A. So which is equal to 2.303 10 raised to the power negative 3 into 0.3979, which is equal to 112.7 minutes. So that is how we can solve. So we'll wrap up this chapter with this assignment homework. So you try it. If you can't, you ask me. You have my number, so you can ask me. Now this one is a radioactive decay problem. As I mentioned earlier, the radioactive decay follows first order reaction, so that is a hint for solving the problem. So that is it for the midterm. We'll still continue with the other chapters as well.